It's a great privilege to be here to honour Charles, and so thank you very much to Wei Lim and to Lewis for the invitation. So this photograph is borrowed from the collection that Steve Stigler took at the 25th anniversary of the Stanford Statistics Department. And there are many other photos of Charles there in sort of less informal settings. Of course, Charles had a huge influence on me, as on many of us. For me, the influence was relatively indirect because perhaps I was too shy. The austere master, although very friendly, so I mostly have influence through his papers. The influence began when I was a grad student at Cornell, working with Larry Brown. And I remember clearly Larry telling me at an early stage how embarrassed everyone was that it had been until the early 1970s to discover the unbiased estimate of risk and the very quick proof that gave after the fact of inadmissibility of the maximum likelihood estimate. And I'll have more to say about Charles's influence on Larry. Yes, so the bulk of the talk is going to be about predictive density estimation. And I will introduce that part of the talk by first discussing the parallels of the predictive density estimation setting with the Gaussian quadratic loss point estimation problem that, of course, Charles did so much to revolutionize. So that part of the talk will be in some way recapitulating things that Molly said on Wednesday, but hopefully that's okay. Then the main point of the talk, more current work, will be that this parallel actually breaks down to a certain extent in the case of the sparse normal means model. And so it breaks down in a sort of interesting way that hopefully I'll be able to talk through. But I'd like to begin by, in some sense, just collecting a list of Charles's papers on admissibility, inadmissibility, and minimaxity for point estimation. So somewhat arbitrarily, I'm going to not mention the papers on testing or on estimation of a covariance matrix. Wei Lim, I'm sure, will talk about the latter on Friday. So there are two reasons for doing that. One is that I will be referring to some of those papers as I go along. And the other is to advertise some slides of Larry Brown's talk in the 2010 meeting, Charles's 90th birthday. His slides are online, and they give a sort of a remarkably authoritative brief overview of essentially this collection of papers. So you can find those slides quite easily. So I'm using magenta to highlight the papers that I'll refer to going on later on. But just to start this list briefly, the 55 paper is a short paper that says that essentially if an estimator is admissible, then you can show that in principle using Blythe's method, although that's far from telling you what to do in a specific challenging problem. Then the 56 is, of course, the great paper on inadmissibility, but it has many other things in there as well. So, for example, there are heuristics around the result. There is a proof of admissibility in p equals 2 for the Gaussian observations using the Cramér-Rao inequality. And there's also and then moving on to the 59 paper, this is a discussion of the best invariant estimator of location under quadratic loss, proving admissibility by Blythe's method again. And then the great paper with James in 1961. The part with James is presenting the actual James-Stein estimator and establishing its dominance over the MLE using non-central chi-squared calculations. But there are other parts by Charles himself. For example, a proof of the admissibility of Pitman's estimator in 2 dimensions, and a discussion of the fact that the natural invariant estimator of a covariance matrix is actually not minimax, and I imagine that Wei-Lim will talk about that. So I've put these in magenta for 2 reasons. The other is that these papers really formed the basis of Larry Brown's PhD thesis, which is a large work that essentially takes Stein's phenomenon, both 2 and fewer dimensions and 3 and higher, and establishes that it works generally for very general loss functions, general location problems, even sequential problems. And there's a lovely quote that I wanted to put up. So Jack Keefer, Larry's advisor, pointed him to Charles's work. And Larry said, well, there were basically 5 papers that I had to read. And these are 3 of them. And the other 2 were David Blackwell and Hodges and Lehman papers on admissibility. And what's also remarkable about these papers is that they are marvels of concision. None of them is more than 20 pages, and most of them, I think, are about 10. So those were the days. So going on with the list, Charles's 1960 paper carried over some of the inadmissibility ideas to a multiple regression setting. And then the 64 paper is as was mentioned earlier by Malloy, I think, a surprising result for a single parameter, an inadmissibility result, and it's the scale parameter of a Gaussian distribution with unknown mean, and the Kullback-Leibler loss function that is now known as Stein's loss makes an appearance there. Then there are 2 lesser-known papers. This one is concerned with a heuristic method for establishing admissibility of generalized Bayes estimators. Somehow there's a relationship to Larry Brown's later 1971 paper, although it's not made very explicit in Larry's paper. And then there's a paper applying the James Stein idea to balancing complete block designs in the analysis of variance. And then, of course, another very, very great paper, which has 2 forms, as we were discussing on Wednesday. The 1974 paper, so these are 2 papers with the same title. The symmetric difference of the paper is 2 papers is much larger than the intersection in terms of number of pages. So Takeru was talking about the estimation of a matrix of means, and that's in the Prague Symposium version. The Annals version, which was written perhaps a year or 2 later, although published in 81, has more material on the James Stein estimate and limited translation and ideas like that. The intersection, of course, is the most famous part, the unbiased estimate of risk itself. And then I've also listed the Leningrad lectures, which were in 1977, but only translated back from Russian into English in 86. These are, from the point of view of point estimation, these are mostly commentary on Charles's earlier works, although it may be the only place where the covariance matrix estimation problem is actually written about in print. And so, no doubt, Wei-Lim will talk about that. Okay, so that's an overview. So again, the magenta ones I'll be mentioning now that we transition to predictive density estimation, which I should emphasize I'm sort of an amateur. Whatever I know about the problem, I've been taught by Gaurav Mukherjee, who was my co-author and former student. We'll see him. So the predictive estimation problem in one formulation is you have past data and future data that are conditionally independent given a governing parameter theta, and one is interested in the predictive density of the future observation given the past. And so this has been widely studied, and one can refer to books, for example, by Aitchison and Dunsmore and Geisser, many applications, and of course a more recent focus on high-dimensional models. What I'm going to particularly focus on is the Gaussian setting, and as I mentioned briefly before, I'm going to focus first on the parallels to quadratic loss estimation, and then move on to the sparse setting. But I want to give a shout out to Ed George, who was, of course, one of Charles's students also, and together with Xinyi Zhu, Feng Yang, and one paper with Larry, wrote quite a few influential papers on the Gaussian predictive density problem. And I'm going to, in particular, be borrowing from this survey that they wrote in StatSci. And then after that, the work is joint with Gurab. And I'll set up the setting by talking about the high-dimensional problem. My goal will be mostly to talk about the establishing asymptotic minimaxity as sparsity goes to zero for discrete priors. So that's our agenda. So now the Gaussian setting, we have a past observation that we have available to us that is multivariate Gaussian with a known past variance v sub x. And then we're aiming to predict a future observation with the same mean, but with a future variance v sub y. And so we want an estimate of this predictive distribution, and a natural way to build that from a prior is by taking the average of the future observation distribution, average with respect to the posterior of the parameter given the past observation that you do have. And so that's called the Bayes predictive density associated with a prior pi. And we'll be focusing on estimators like this. And so here it is written again. So the reason, one of the simple ways to see that one might believe that there are parallels between the predictive estimation problem and the point estimation problem is that the mean of the predictive distribution, just by easy Fubini theorem, is given by the mean of the posterior, and so the mean of the predictive distribution is the same as the posterior mean, which is, of course, the Bayes estimate for squared error loss. So that immediately suggests that you are going to get intuition from the point estimation problem. And then, as I said, later on we'll be assuming that the parameter theta vector is sparse and, in fact, drawn from this spike and slab or sparse prior distribution. And so one can draw little graphical models to sort of emphasize what's observed and the conditional independencies. And I will be moving between univariate and multivariate versions. So in the univariate version, there's just x and y conditionally independent given theta. And then the multivariate version has a plate here for the NIID replicates of this univariate problem. Still you observe this. And the replicates are governed by these parameters, the past variance, the future variance, and here the sparsity. But we'll see that more explicitly later. Just another way of showing it. So in warm-up, some examples of predictive densities, very simple ones. The plug-in one is, in some sense, almost the simplest, and so you take the density of the future observation, and in place of the parameter theta, you plug in an estimate of the mean that you've obtained from the past observation. And the main thing to say about this estimator at this point is that it cannot be a Bayes estimator. That's relatively easy to establish in the Gaussian setting, but I won't talk through it. So the plug-in estimate centered on the observation, the future variance, but not Bayes, or even generalized Bayes. So now if we look at examples of Bayes predictive densities working with the conjugate prior family for simplicity, One end of the conjugate prior family is a point mass at 0. And so if you're absolutely sure that the mean is 0, then your posterior is still sure that the mean is 0. And so the predictive distribution is actually just the future observation distribution at mean 0. In some sense, at the other extreme, the uniform vague prior leads to a posterior distribution centered at the maximum likelihood estimate, generalized Bayes estimator for uniform prior. And the future variance is the sum of the past variance and the future variance. So that's the uniform predictive density estimate. And then in between the two is the conjugate family with where the prior variance here is parameterized so that the posterior mean is a linear shrinkage. Multiply the data by alpha between 0 and 1, and that takes us from variance 0 to the vague prior. And the effect on the variance is a little messy here, but the predictive distribution variance is the future variance plus alpha times the prior variance. So just a one parameter family, but centered on the posterior mean. So decision theoretic evaluation of predictive density estimates. I think the initial use of Kullback-Leibler as the distance or loss measure goes back to Aitchison in '75. There are also information theoretic justifications. And so in the loss function notation, theta is the parameter and the action is the estimated predictive density. And here's the KL divergence between the two. To get a frequentist risk function corresponding to unknown theta, one averages over the past observation distribution. So this gives us a Kullback-Leibler risk. It was shown by Aitchison that the Bayes estimator for this KL risk is indeed the predictive Bayes density that we described earlier, the posterior expectation of the future distribution, expectation against the posterior density. So that is sort of a natural thing that goes along with the KL loss function. So now we have the definitions to start to talk about the parallels between quadratic estimation for the point parameter theta and the KL risk for the predictive distribution. And so, just to recall the most basic facts for the quadratic estimation of a multinormal mean theta with the known variance v sub x and maximum likelihood estimate x. So essentially the non-trivial properties here were all due to Charles. So as I mentioned earlier on, the admissibility in the Gaussian case for p equals 2 and the inadmissibility for 3 and larger are in the 56 paper, and the 59 paper extends this to location families, and the James Stein paper, as we discussed, has the James Stein estimator. The parallels for predictive density estimation, we now have our future observation and the future variance here and the KL risk. And these properties are, in some sense, exactly parallel. Especially the admissibility results appear in this paper of Brown, George, and Su in 2008. So the parallel is between the maximum likelihood estimate and the uniform prior predictive density estimate. So the mean of this predictive distribution is the MLE. So developing the parallels a bit further, in the point estimation problem, there is the representation of a general Bayes estimator as a perturbation of the maximum likelihood estimate. In recent years, this has being called Tweedy's formula, but in some sense it was Larry who made sort of the most astonishing and profound use of this in discussing admissibility in the multinormal mean problem. So here M is the marginal density of the prior pi, and this the logarithmic gradient. And so there's a remarkably analogous result established in the 2006 paper of George Liang and Xu, which says that if we look, for example, at the ratio of the predictive density estimate for a general prior pi relative to the uniform prior predictive density estimate, then that can be described in terms of the ratio of two different marginal distributions, sort of analogously to this logarithmic derivative here. The denominator is the marginal distribution of the observation at the past variance v sub x. And then for the numerator, we introduce an important quantity, which is if we imagine that we observe both x and y, then the minimum variance combination of those two observations is this, which we'll call W. And the variance, and that optimal variance for the what you might call the oracle combination, since you don't actually have y, that oracle variance is, of course, smaller than v sub x, and the extent to which it is smaller is obviously a key parameter depending on the value of v sub y. So the numerator in this representation is the marginal for a prior pi and this observation W. And so again, there's a representation of a general Bayes estimator in terms of the uniform prior one. So going further with the parallels, so the unbiased estimate of risk for quadratic point estimation of Charles compares the maximum likelihood estimate and and a general estimator, but if you plug in a Bayes estimator, then you arrive at this representation in terms of the Laplacian of the square root of the marginal density of the observation. And so it's this that for example, this is certainly Stein's result. I've mentioned Brown because if you, for example, take the harmonic prior as was discussed on Wednesday, then you very easily, using this formula and Brown's representation, show that that it dominates the maximum likelihood estimate. And so again, the remarkable parallel is that there is a similar result for predictive density estimates, now involving an average over variance scales from the past variance down to the oracle variance, which remember was smaller. And so this means an observation with mean theta and variance v within this range, and otherwise the same ratio. So a really important paper was that of Komakis in 2001 that showed that the harmonic prior led to a predictive density estimator that dominated the uniform prior predictive density estimate. And Ed always emphasizes how important this paper was. And then a posteriori, with this representation, one can relatively easily see this domination. So Komaki's proof was a direct proof, and this came later. So finally, with parallels, there in the 2008 paper, there's a mixture representation. Again, we have our past observation, future observation, and oracle variance. And if we look at intermediate variances and have a notation for the point estimate quadratic loss mean squared error of a Bayes rule, then the KL risk is actually a weighted average of quadratic estimation risks with this inverse weighting here over the range of variances from the oracle variance up to the past variance. And so the predictive risk is a weighted average of quadratic risks. And so all of this is pointing in the direction of a result that holds for quadratic estimation should carry over to KL risk. Okay, so now let's move to a sparse estimation problem. So now we're setting up a high-dimensional situation that is sort of as simple as it can be, where we essentially assume independence of the observations, and therefore the predictive density would factorize. The KL risk of the joint predictive density it becomes an additive decomposition of univariate risk functions of the ith components. And we'll consider sparse vectors of means, where sparsity is in the now standard sense of counting the number of non-zero entries. So S will be the number of non-zero entries out of M, S typically being small. And so, a motivational example actually taken from the paper on call center data of Larry and Avi Mandelbaum and others. So you might imagine that you have information over the course of a day of the volume of calls into a call center. That varies about some mean function for typical days, and you want to predict the volume of calls on a future day. And you might imagine that in some wavelet basis, that theta might have a relatively sparse representation, and that these guys might be more or less independent. And so that brings us into the sparse product model that I mentioned. And so now the question that we ask is, what can be said about the KL risk of a predictive density estimate under these sparsity assumptions? So again, I'm going to emphasize that there's a multivariate problem and there is a univariate analog, and to point out why we move between them. If there's a sparse vector of means that has at most S non-zero components, then most of the components are zero, and so the multivariate risk function is really mostly composed of the risk function at zero and then S non-zero contributions here. And so the maximum of the multivariate risk is actually composed of two terms, one for the risk at zero and then one multiplied by the number of non-zero terms and the maximum of the univariate risk. And so we'll be working with the univariate risk primarily, because this is typically much smaller, and so this is usually the dominant term. So a lot of the time you'll see me talking about the univariate problem, but that's the reason is captured here. So some years ago, Gurab and I looked at the minimax risk in this setting. And to describe the result, I want to emphasize that from now on, we're going to just make the convention that the past variance is 1, and so the key parameter is going to be the ratio of the future variance to the past variance, and I'll call that R going forward. And so the problem is in some sense harder as R gets smaller, as we will see. And so the minimax risk in the situation where the sparsity is asymptotically vanishing, so non-zero components, a negligible fraction of the total number. So at a gross level, it's what one expects in these problems, namely proportional to the number of non-zero terms, with a logarithmic penalty because you don't know where the non-zero terms are, where the non-zero the S non-zero terms are amongst the n coordinates. But if one wants to look at the constant in front, then it's helpful to parameterize in this way. So e to n is the sparsity fraction, so this is the non-zero number. And an important role is going to be played by what I'll call the predictive scale, which is twice log of the sparsity fraction inverse multiplied by this oracle variance. And so the minimax risk is given by this squared predictive scale divided by 2 over r. And so smaller r, harder problem. And now let's compare this to the quadratic estimation problem, sort of now fairly standard result, that if you are estimating sparse mean with independent coordinates and quadratic loss, then the minimax asymptotic risk is twice Sn log n over Sn. And the corresponding scale, and I want to contrast these, is 2 log e to n inverse. So this is essentially the square of the universal threshold for sparse point estimation problems. And so this predictive scale is smaller because VW is this oracle variance, which is less than 1. And so let's try to talk a little about why the predictive scale is smaller than the estimation scale. So here's the estimation scale, here's the predictive scale. So with sparse estimation, so imagine for a moment that the observation variance for the past observation is 1, and that we're dealing with a sparse prior, so most of the prior probability is 0, with a small amount at the estimation scale lambda e. So the posterior is also mostly at 0 until the observation is at this threshold or larger. And so essentially the posterior mean is going to be 0 unless the observation is so large that suddenly the posterior actually overrides the preference for 0 and declares that it could be at the larger value. And so informally we could say that values of the parameter between 0 and the estimation scale are invisible from the point of view of point estimation for this prior. And now we can scale that for variances v between 1 and the oracle variance, and the intersection of all of those invisibility regions is given by this prediction scale, lambda f, as opposed to lambda e. And then if we bring in a sparse prior at the predictive scale and use the fact that all of these variances between oracle and 1 will lead to invisibility for this value, so a squared error of lambda f squared. And if we put that into the mixture representation, we see that the KL risk is going to be actually bounded below heuristically by essentially lambda f squared here, which simple calculation gives the minimax risk before. So this is one way of arguing that the right scale for arriving at the minimax risk is the predictive scale lambda f, which is smaller than the estimation scale lambda e. So we're going to, the task now is to look for asymptotically minimax Bayes rules, and to make that more concrete, let me say that the earlier result with Gurab was certainly not a Bayes rule, because it was to show that the bound was achieved. We used a discontinuous estimator that involved a thresholding structure. So there were 2 different predictive density estimates and sort of uniform predictive estimate for large values and a certain other one for small values. And so it's clearly discontinuous, clearly not a Bayes estimator. So now we want to find Bayes estimators that are asymptotically minimax. And so that's the goal for the next little bit. And the key tool is going to be a risk identity that relates the risk of the predictive Bayes estimate to something, the future observation at 0. And so here it is. This is relating risk for a general estimate to a risk of an atom at 0, the estimate corresponding to an atom at 0. So that corresponds to a quadratic term. So in comparison to the earlier result, which related to the uniform prior Bayes estimate, this is relating to the atom at 0 prior. But that's the natural thing to do for a sparse situation, because you're looking at a deviation from an atom at 0. And so there's a decomposition in terms of numerator and denominator terms that involve mixtures relative to this slab part of the prior. So this is relatively explicit to work with. And so that makes these computations relatively tractable. And one can apply it to so-called uniform slab priors, where this is a uniform density, and as I'll focus on more, cases where nu is discrete, in particular countably discrete, as I'll explain. So let me spend one slide briefly, because of the time, on the uniform slab situation. I don't want to talk through this. The main message is that if you have a uniform slab with careful choice of the size of the slab, in most cases one can arrive at an asymptotically minimax estimate, but you have to be a little careful about the size of the slab. So the risk decomposition leads to this result for uniform slabs. Let's turn to the discrete prior, because this seems to me a little more, at least technically interesting. And so general decision theory says that if we're looking for a minimax estimator, then it will be Bayes against the least favorable prior distribution. And if it's minimax, the risk function will be bounded. In this Gaussian situation, the risk function will be an analytic function. And so the places where this risk function achieves its maximum has to be a set, because it's analytic, it has to be a set without accumulation points. And so it has to be a countable discrete set. And then furthermore, the prior has to be concentrated in the points of maximum of the risk function. So there's a characterization, not concrete, of what the least favorable prior has to look like. It's going to be in a discrete set concentrated on the maxima of the corresponding risk function. But of course, this is not something that's accessible except by complicated numerical optimization for a fixed sparsity eta. And so if we let the sparsity go to 0, we can hope to find a simpler description and an asymptotically minimax formulation. And so we hope to find a sparse spacing where the spacing of these atoms spreads out, and that hopefully will give us some periodic structure and an easier analysis. And the sparsity and the wide spacing leads to tractability in this way. So the prior distribution, we're going to imagine, so the prior is in blue, and it's discrete on these atoms, and it's decaying somehow geometrically. But the posterior, of course, comes from the prior in the usual way, and the effect of a large spacing between the atoms is that for any particular x, it's plausible and provable that only the neighboring points are really going to matter in the posterior. So the posterior in red is really at mostly 2 points, and then further away it's much smaller for large spacings. And so the notion is that one can actually do calculations with a 2-point posterior. So being Australian, I look at this red picture and I think of Australian rules football. And you have the big goalposts and then the side ones for the behinds. And because this is not widely known in the world, I found a little helpful thing in French for the francophone world that tells you what the score is for each of these. But anyway, this is what the posterior looks like. And so we can hopefully use that to sort of get at approximating this distribution. And the first thing to ask is, well, where is the first atom going to be? If it's minimax. So here's that picture, and in order to figure out what the spacing of the first atom is, we can do an initial calculation with a 2-point prior, and we're going to ask, well, what multiple of lambda, which is going to be this predictive scale going forward, what multiple is indicated for least favorable? And so the risk function is going to be sort of essentially 0 at 0 because there's so much prior mass there. So the main attention will be on the risk function here. And so one can evaluate that, and it's some function of this spacing A. And the only time that this function sigma A, I haven't written it explicitly, the only time that this gets up to the level that we need for minimaxity is if A is equal to 1. So that justifies the notion that we should be working on this predictive scale, and that the spacing of the first atom should be at lambda f, the predictive scale, and not the estimative scale. But that's only the first atom, so what happens after that? And we're trying to make things simple, so it's reasonable to try to use a uniformly spaced grid with spacing lambda f, and to use a geometrically decaying set of prior weights. And if you do that and use the posterior 2-point heuristic, you can calculate the rescaled version of the risk function. So we're scaling the horizontal axis by lambda and the vertical axis by lambda squared over r, and the risk function of interest is this blue function here. And it turns out that it has a maximum lambda, but it turns out that between lambda and the second point, there is an interior maximum. And so here's the point where interesting things happen. This interior maximum has a value given here. So gamma sub r is 2r plus 1 over 2r plus 2. And the point is that, of course, we're not minimax. We're out of luck if this is larger than this. And so we want this maximum to be 1. And that occurs if and only if the future to past variance ratio is larger than this quadratic solution of a quadratic equation. It's about 0.3. So if the future to past variance ratio is too small, below this, then the problem is too hard, and the uniform grid prior is not asymptotically minimax. So this is where the parallel breaks down. The natural. So let me explain why the parallel breaks down. If we go back to point estimation, if we use the same kind of equally spaced discrete prior for squared error loss, using the estimation scale now, then this is indeed asymptotically minimax. It's even asymptotically minimax to higher order, but that's not germane here. And so, in some sense, this uniform grid prior, which works perfectly well for point estimation, does not work in the difficult cases for the predictive estimation problem. So here the parallel doesn't quite fully work. So how do you get minimaxity in the subcritical case, if you like, the small values of R, small values of future variance? Well, the hint, of course, comes from this picture. You say, well, how do I get this down? How do I get this risk down? Well, the problem is that the spacing is too large. There's too much space between these two support points, and therefore this risk gets up. So clearly we have to move this down. And so that's the prescription. Change the grid spacing to be narrower, So make the grid spacing some parameter b less than 1 as you go up from lambda. Now, I emphasize that this still stays at the predictive scale lambda sub f. It's just to the right of that, where the influence of 0 is less felt, that you have the narrower scaling. And eventually you can switch back to the predictive scaling after some switch point. But inside this sort of inner range, if you like, the inner intervals, we want to have narrower scaling. And so if we adopt that and make a corresponding change to the decay weights of the priors, so I've shown this on the log scale to sort of show that the ratio of the priors goes down by b squared times lambda squared in the inner case as opposed to lambda squared in the outer case. So with that variant, now the maximum risk in the inner setting, you have this smaller quantity, and so if you make this small enough, you're going to make this below 1, and everything's going to be copacetic. And this is a sort of a generic picture that shows that the main issue is this second interval, and if you can get this point down, which is can be achieved by making this b smaller, then you're going to be okay. So that's essentially the end of this story, that if you make the inner spacing small enough, and that small enough depends on this future to past variance ratio, for large values of R, this will be greater than 1, and you'll be back with uniform grid, and so the uniform grid prior will be fine, but for small values of R, you need this smaller spacing. But then asymptotic minimaxity results. So we're still revising this, but it's in an archive posting. There's more to understand about these discrete priors, but to bring this back to Charles, Brad Efron has this quote that I think is quite well known from Gustav Elving when he was visiting Stanford, that you know, after I met Stein, I wondered why anyone else did mathematical statistics. Larry Brown probably wasn't thinking of that quote at the time, but he said it better than, we've heard it said many times here, but he said it better than I can say it in his 2010 talk, that Charles was so generous in sharing his ideas, and they have given us so much to work with that's at least one way to reply to Elving's question. So with that, I'll thank you very much. Yeah. Well, so what I'm doing here is quoting from Brad's obituary notice in the JRSS, his obituary notice for Charles, and he attributes the quote to Elving. So Elving visited Stanford in the 1970s. So I think that's what you're referring to, or you think even before that? No. Brad didn't say it. Elving said it. Oh, Brad has reported it many years ago. Well, maybe David has a more concrete recollection. Hmm. Yes. That's. So I mean, I don't mean to suggest that Larry was explicitly replying to the Elving quote, but I'm using it as a reply because I think it's correct.